G'day viewers. In this segment we'll talk about contention-free multiple access, an alternative design to the method of multiple access used in Wi-Fi and classic Ethernet. So in Wi-Fi and classic Ethernet, the multiple access problem is solved with randomization. What we'll talk about in this video is a completely different technique which is based on taking of turns. So in this picture here, the four nodes might take turns from left to right, 1, 2, 3, 4, to send to the access point. Before we get into the design of turn-taking multiple access protocols, one issue we need to talk about a little bit is why we would bother. Why aren't random multiple access protocols good enough? If they were, after all, there's no need to worry about these different turn-taking protocols. Well, it turns out that CSMA, the carrier sense multiple access method we looked at for Wi-Fi and Ethernet, is good under low load. It's very effective there. And the reason is that it grants immediate access, so there's no delay. And under conditions of low load, few collisions are expected, so the overhead is very low. But the issue, and the reason we're talking about turn-taking multiple access, is this bullet here. Randomized schemes are not so good under high load. The issue is that under high load you expect collisions, and this leads to a high level of overhead. It's also the case that the access time varies. A node, when it tries to send, might get lucky, try and send and get its packet off right away, its frame off right away. Or it might get unlucky. It might suffer repeated collisions, and so it might take a long time for its frame to be sent. We would like to do better under conditions of high load. With turn-taking multiple access protocols, the protocols define an order in which the nodes send. The order is really an opportunity to send. It's a chance to send. So if you have a frame, when your turn comes around, you get to send it. If you don't, you just pass, and the next node gets its turn to send a frame. All we really need to do to come up with these protocols is to devise some ordering. I'll talk about one on the next slide, a method called token ring. But you can imagine other methods. For instance, the nodes could use their addresses to impose an ordering from lowest to highest, or vice versa, in terms of who gets to send next. So with token ring, the physical topology is used to provide the ordering. The nodes are wired together in a circle, in a ring. And then a special frame called the token is put on and sent around the ring. You can see the token here. And it's going around the ring anti-clockwise. As the token passes the nodes, it gives each node who has the token an opportunity to send. They grab the token, then they, instead of sending it on, first of all they send their frame, and after their frame has been sent, they then pass the token on to the next node, further along. So the sending order here is going to go 1, the token will go on to node 2, to node 3, 4, 5, 6, 7, 8, 9, and then we're back, and so forth. That's our order, and that's token ring in a nutshell. This kind of turn-taking protocol, token ring, as well as other turn-taking protocols, do have advantages. In this scheme, there is a fixed overhead with no collisions. The collisions are gone as a source of overhead, and in particular, we won't have an increasing number of collisions or a large number of collisions as the load gets high, just the fixed overhead. Because of this, the turn-taking protocols are more efficient under high load. We also get a regular opportunity to send. This leads to more predictable levels of service. You know that you'll get to send a packet every, say, 100 milliseconds or so. And the concept is easily extended to different qualities of service. As you might imagine, we could just allow one node to send, say, 2 frames every time it got an opportunity to send, instead of 1. That way, we get to send twice as much traffic as another node, if it was a high priority node, for instance. There are some disadvantages, though. And the principal disadvantage is this, complexity. There's more to this protocol, defining the ordering and imposing it, and that means that there's more to go wrong. What could go wrong? Well, just as an example, what would happen if the token was lost? Now, this really shouldn't happen. The token's just a frame going around the ring, but unexpected things can happen occasionally. Let's just suppose that the token is corrupted by bit errors, and it's too corrupted for any error correcting code that's used down there to deal with, or even an error detecting code to recognize that the token's in error and allow it to be repaired. If that were the case, the token might suddenly appear to disappear, and then the whole protocol would lock up. And if you can't send until you've got the token and there is no token, boy, you just never get to send. That would be no good. So we'll obviously need to guard against that. How? Well, token ring protocols in practice have every node have extra machinery to guard against these kind of failures. Nodes might run a timer, for instance, and if they haven't seen a token for a long time, they might decide there's been an error, and the nodes would collectively mint a new token. They'd work out who would do it. They would have to coordinate so they didn't have to have multiple tokens, and so forth. You can see that even though losing a token is a rare case, it can add considerable complexity to the protocol. There's also somewhat higher overhead at low load. The overhead of token ring is fixed, just passing that token around, but it's non-zero. And at low load, CSMA or randomized schemes have almost no overhead whatsoever.